Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 16, 2025, which was about 5 days ago. The standout result is an efficient universal predictor that does not identify the true system, yet still guarantees vanishing per step error for many marginally stable nonlinear dynamics by competing with powerful linear observers. The paper is titled Universal Learning of Nonlinear Dynamics, and as we will see later, the implications for long-horizon prediction are quite significant. In short, the authors introduce observation spectral filtering and a learnability measure called Q-star that together drive rigorous online guarantees across noisy, partially observed systems. Building on that, the leading tweet expresses excitement about an efficient method for learning marginally stable nonlinear dynamics and links the preprint, highlighting student collaborators. Engagement looks modest, with about 57 likes and a few replies. Alright, we are looking at a comparison table that lines up methods for learning linear dynamical systems against 4 capabilities. The table shows columns for marginally stable handling, hidden dimension-free complexity, asymmetric dynamics, and adversarial noise. You can see that observation spectral filtering checks all 4 boxes, which matters because it stays efficient while tolerating asymmetry and hostile disturbances. By contrast, classic spectral filtering misses adversarial noise, and closed-loop regression depends on hidden dimension. The USP method partially covers asymmetry, but still lacks adversarial robustness. Next, we are looking at a 2-panel figure that plots instantaneous loss over steps for 2 linear system setups, with blue for classic spectral filtering and orange for spectral filtering with observation filtering. The left panel shows the random system with disturbances, where both methods drop quickly, but the observation filtering curve settles much lower because it handles correlated noise. The right panel shows the permutation system, where the blue curve stays flat at high loss, while the orange curve slowly grinds towards 0, which reflects the large Q-star and long refinement phase. Now we are looking at a 2-panel figure that plots Lorentz trajectories in 3 dimensions, which illustrates the classic double lobe attractor. The full graphics area contains 2 separate 3D plots side by side, so we can compare paths from nearby initial conditions. You can see the left panel starting near a red star and spiraling toward one lobe, then swinging across to the other, showing sensitive dependence. The right panel follows a nearby start, yet its path diverges quickly, which highlights the chaotic nature that later makes partial observation challenging for the baselines. Moving to the results, we are looking at 2 loss curves for the Lorentz system, with full observation on the left and partial observation on the right. The graphics show instantaneous squared error on a log scale over steps, which lets you compare decay rates across methods. You can see the red spectral filtering with nonlinear observables steadily dropping to the lowest band, while the green spectral filtering also improves but plateaus higher. Meanwhile, the blue linear dynamical system baseline wanders and inflates under partial observation, which highlights the benefit of time aggregation. Now we are looking at a 2-panel figure comparing prediction loss on a double pendulum, with full observation on the left and partial observation on the right. You can see loss on a log scale over steps, so downward curves mean better predictions. In the left panel, spectral filtering with nonlinear observables sits lowest, while spectral filtering alone is close behind, and the linear dynamical system rises sharply late. In the right panel, spectral filtering methods remain strong under partial observation, whereas extended dynamic mode decomposition stays higher and the linear dynamical system occasionally collapses. Building on those results, 2 takeaways stand out. First, spectral filtering with observation filtering delivers stable, noise-robust prediction even under partial views. Second, learnability hinges on the Leuenberger program's condition Q-star, which quantifies how hard favorable eigen placement is. A Leuenberger observer means a feedback-based state estimator. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.